Okay. 1.6 is on predicates and quantifiers. Okay, a predicate, a logical statement, whose truth value is a function of one or more variables. Okay, so okay, let's take a sample predicate here. So the predicate P of X, we're going to define as X is an odd number. Okay, so X is an odd number. Okay, if I put 5 in there for X, okay, is this a true statement or a false statement?
True.
Okay, Eric says true. Everybody else say true? Okay,
True.
is true since 5 is odd. Okay, let's look at another predicate. Q of xy is x squared equal to y. Okay. So if I took Q of 525, okay, we would say that is true since 5 squared is equal to 25. Okay, if we look at R of x, y, z is equal to x, whoops, is equal to x is defined as, this colon means defined as. Okay, R of xyz is defined as x plus y equals z. Okay, we know for R of 236, is that guy true or false?
False.
Okay, thank you, Eric. Thank you, Anthony. Okay, anybody else? Okay, want to get on the board? Okay, false. Okay, because 2 plus 3 does not equal 6. That is false. Okay, the domain. Thank you, Thomas. Nice to see you. Glad you have joined us. Okay,
Thank you.
welcome. Okay, the domain of a variable is all possible values for that variable. It is all possible values for that particular variable. Okay. For P of X, where X is an odd number, okay, the domain of X is all integers okay, is all integers. Okay, the domain of X, let's just say X. Okay, the domain of X is all integers. Okay, so okay, we plug in these integers X and we just test them and see if they're odd, but it's all integers. Okay, would be the domain. Okay, this is because only integers can be even or odd. Okay, this is because only integers can be even or odd. Okay. Are predicates always capitalized? I believe so. Yes. Okay, a predicate. Whoa, hello. A predicate contains a variable okay, whereas a proposition does not. Okay, so a predicate contains a variable, whereas a proposition does not. Okay, let's talk about quantifiers. The universal quantifier okay, and this kind of looks like an upside down A, okay, or it's an or symbol with a line through it. Okay, the universal quantifier okay is read as for all or for every. Okay, it's read as for all or for every. Okay, it means everyone in the domain has to have this certain trait, this certain characteristic. Okay, it's for all, for every. And this is the symbol. It's an upside down N. Okay. Okay, if we say for all X in P of X, okay, this is read as for all X P of X, okay, this is now a proposition since all values of X in its domain are used to evaluate its truth value. Okay. So you're like, but it's P of X, right? Just think of it this way. Okay. So if I say that we have for all X, okay, think of that as D, the domain, right? For all X, that's the domain, right? And so then what are we doing with that domain? We're putting it in, okay, to our predicate. And so it's no longer has a variable because we're saying all of these values have to satisfy this condition, this predicate, and so it no longer has a variable. It doesn't vary anymore. We know exactly what those values are. And that those values are treated as a single unit. Right? So does the single unit have this characteristic or does it not? Okay, if you want to use kind of, some visual understanding here, I could say, well, this is 1, 2, 3, 4, 5, right? Okay. And so, whereas if I had P of X and I said, let X be all numbers, or X is a number less than 10. Right? If X is a number less than 10, then we say, oh, okay, we could try each of these values and say, well, is it less than, X is a number less than 10, right? We could plug in, 1, 2, 3, 4, 5 into each of these, okay? Or I could say for all X in the domain, X is a number less than 10. Now, what is that saying? That's saying all of these are treated as one grouping, and I put all of them in, and I get a truth value for all of them. So would this truth value for all X, P of X, would that be true or false?
True.
Yeah, it is true. Why? Why, Thomas?
Because every number in the domain is less than 10, which is part of our
Yeah,
requirement.
exactly. 1, 2, 3, and 4, and 5, they are less than 10. I have no value in my domain that is less than 10. Now, if I had, say, 21 over here, now it would be false, right? It's true or false. We don't have to test every single one of these. Okay. Okay. Every single predicate, okay, all the values, we just have to, we take this as a whole unit and say, okay, are all the values a certain characteristic? Okay, without the 21, it's true. With the 21, it would be false. So we can get a truth value for the whole thing. The whole enchilada. Right? So we're taking this guy as a whole, and we're saying, oh yeah, that's true. That's true as a whole. That's called a universal quantifier. We've taken the universe of values, which is the domain, and we treated them as one unit and said, oh, do all of these values have this characteristic? Okay, and so that's why it's no longer, okay, it's no longer a predicate, it is now a proposition, because the variable is no longer X, the variable is the entire domain. And it's taken it as a whole value. You can call it D, you can call it C, whatever you want to call it, it's all of those values together. Okay. The way that we can write this formally is that for every X, P of X is logically equivalent to P of A1 and P of A2 and ... all the way to P of A sub n for all a sub I in the domain of X. Okay, we're taking the and statements, the conjunctions of every single one of these values in the domain, and we can write it as either true or false. If they're all true, then they're true. If only one is false, then it's false. Then it falls apart. Okay. Okay, example 1. Okay, prove that for all x, 1 over x plus 1 is less than 1 is true for any positive integer. Okay. Okay, so let's show that this is true. For all x, 1 over x plus 1 is less than 1. Okay. So what I want to do is I want to kind of do some scratch work here. Okay. I want to do some scratch work. I want to do some thinking on how am I going to prove that this is true for any positive integer. Okay. Okay, so if I were to rewrite this as 1 over x plus 1 is less than 1, and I were to multiply both sides by x plus 1, then I would say that 1 is less than x plus 1, right? And if we were to subtract off 1, then that would be 0 is less than x, which means that x is greater than 0, right? And what is it? What is x greater than 0? Well, that's a positive number, right? So let's think about this for a second. If I went in reverse order here, I could actually prove what I want to prove, right? So if we say proof, let x be a positive integer. Okay, then what does that mean? Okay, that means that x is greater than 0, right? Isn't that what that means? Okay, what would happen if I added 1 to both sides? Okay, by definition of positive integer. Okay, if we add 1 to both sides, we get x plus 1 equals 0 plus 1. Okay, and that's just adding 1 to both sides. That's additive. That's just the property of addition. Okay, and then this is going to become x plus 1, okay, property of addition. Okay, x plus 1 is greater than 1. That's just simplifying. I would actually call this the inequality. This is from algebra. Inequality property of addition. Okay, that's just algebraic property. Simplify, okay? And now let's divide x plus 1, both sides. Okay, and we get 1 is greater than 1 over x plus 1. Okay, how did we do that? That's by division property. Or well, I'll say the inequality property of division. We don't have to worry about whether or not the inequality is going to flip. Why is that?
Positive numbers.
Yeah, thank you, Eric. Because they're positive, x is defined as a positive value. Right? Let x be a positive integer, then we don't have to worry about any dividing by any negatives, right? So that's a positive thing. Look at that. We're staying positive. Okay. Okay, let's write this as 1 over x plus 1 is less than 1. So this is just a property of inequalities. Okay, it's actually called the symmetric property of inequalities. Yeah, I don't expect you to know those justifications. Okay, this is not an algebra class. It's just that's a logic class. Okay. Okay, but some of our examples will be based on algebra. Some will be based on geometry. Some will be based on English language. Some will be based on scenarios. So just however. Okay. So we get the 3 dots now. Does anybody know what the 3 dots means? I'm sure Alan does. Alan, what do the 3 dots mean? Yep, therefore, exactly. So it means therefore. Okay. So therefore, for all x, okay, for all positive x, for all x, such that x is a positive integer, 1 over x plus 1 is less than 1. And then I put my little square, which means QED, quod erat demonstrandum, stratum, demonstrandum, I think it's a D. I have it written down. Quod erat. It's quod erat, QUODERAT, quod erat demon, like demon, demonstrandum. Like strandum, there we go. Quod erat demonstrandum. It has been proven. It has been demonstrated. Okay. It just makes it sound, so much, more regal and definitive by, you know, saying it in Latin. Like, okay, you know, it will be like this for all of time and forever. It has been demonstrated. Quod erat demonstrandum. Oh, there we go. Okay, that's what this little square means. Okay. Or if you ever see QED on a proof, it's the same thing. They just don't want to write out, you know, quod erat demonstrandum. It's kind of long. Okay. Okay, but yeah, the three little dots, they mean therefore. Okay, what are those three little dots? Therefore. Okay, sorry, it's a bad joke. Okay, the three dots are there for therefore. Anyway, whatever. Okay, there aren't a lot of jokes in math, so you know when you take one, you have to take it. When it just comes up, you're like, I'm gonna have to take it. Okay, so okay, counter example. What's a counter example? Is an element in the domain okay, that shows the predicate as false. Okay, it shows the predicate as false. Okay. Okay, for example, if we let P of X be equal to, be such that X squared is greater than X for positive integers, then for all X, P of X is false. Okay, why?
Couldn't one be used as a counterexample?
Because what?
Like one could be used as a counterexample?
Yes, exactly. One, prove this thing as false. All of the values work except for one. One, because it is part of my domain, it's a positive integer. Okay, one does not work, and therefore the whole thing does not work. Okay, so let x equal 1 be our counter example. Okay. The existential quantifier, okay, and this is, it looks like a backwards E, okay, is read as okay, there exists. Okay, there is an element, there exists. Okay. Okay. Okay, the existential quantifier, okay, is read as there exists. Okay, so there exists X. Okay, there exists X okay, such that P of X has a certain condition. So this is red. There exists an X such that P of X, okay, such that the condition P of X is either met or isn't met. So for the universal quantifier, it's for all. It's for every one of the domain. But it's opposite for the existential quantifier. The existential quantifier, we're only looking for one to make it true. Okay? And if there is none, then it's false. So only one to make it true, but if none exists, then it's false. So it's kind of the opposite of the universal quantifier. It's the complement, as you would say in logic. The complement is of the existential quantifier is the universal quantifier. And the complement of the universal quantifier is the existential quantifier.
Professor,
Yes.
I'm so sorry. Can you scroll up just a little bit so we can see the top statement? Yeah, there we go. Sorry. Thank you so much. I missed that part.
Okay, so we can write this existential. There exists an X such that P of X is logically equivalent to P of A1 or P of A2 or ... P of AN for all AI in the domain of X. Okay. Okay, for the existential quantifier, okay, a value in the domain that shows the predicate as true is called an example, as opposed to a counterexample, right? So a counterexample shows the universal quantifier as false. An example shows the existential quantifier as true. We only need one counterexample to prove everything false, whereas we only need one example to prove something is true. Okay, however, if we want to show that there exists an X such that P of X is false, then, oops, come on, bro. Okay, then one must show what? If we want to show that this is false, that there isn't one that exists, then what do we have to show? What do we have to go through? We have to go through and systematically show that every value in the domain does not work.
The universal quantifier?
No. No, we're saying that in order to prove that this thing is false, that there does not exist any single value that would make this true, we would have to go through and systematically look at every single value in the domain and throw it out. That's the only way that a existential quantifier is proven false, is that we cannot find any example. There is no example that we could pull out from the domain that would make it true. We must show all domain values give a false proposition. Example 2. Okay, show that there exists X such that X plus 1 is less than X is false for all positive integers. Okay, so let's prove this false. Or let's just show this false. We're not going to do a formal proof. Just show this false. Okay, how can we show this false? Well, let's take X plus 1 is less than X, and let's subtract off X. What do we get? We get 1 is less than 0. Okay, which is false, regardless of X. Right? Therefore, we have shown that no matter what value of X you plug in there, it's not going to work. So in one fell swoop, we have shown if we take all of our domain, any value in our domain is not going to work. Okay, therefore, the inequality is false. And okay, there exists, okay, and the proposition that there exists an X such that X plus 1 is less than X is also false. Okay. Okay, example 3. Okay, is there exists an X such that X minus 1 is greater than 0, true or false? Okay. Okay, what do we need for this? We just need an example. Okay, we just need a value that works. Okay. Is this true or false? Let's put in 4 positive integers. Let's define our domain. Okay. But so for positive integers, is this true or false? Okay, well, let's just try, I don't know, let's try 3. Let x equals 3. Then what happens? We get 3 minus 1 is greater than 0. That's 2 is greater than 0. Is that a true statement? It's true. And because we only need a there exists, all we need is to find one that works, then the statement is true. It's true.